In a previous video, we talked about how programmable I/O can be used to convert any of the GPIO pins on the Raspberry Pi Pico to use any communication protocol we want. So if we don't have enough UART ports, we can use the magic of PIO to just make some new ones. But we only talked about the theory and not the implementation. So in today's video, I'll give a high-level overview of the structure of a Pico project using the Pico's C language SDK. In a project that uses PIO, there are three key components: the PIO program, written in PIO assembly, then a main program, written in C, and finally, a CMake file that generates the build script, called the makefile, that combines all the files in the project into a single program binary. The PIO program lives inside one of the state machines in the PIO core, which, if you remember, are like little processors independent from the main CPU. You could run several PIO programs on multiple state machines at the same time. Then there's the main C program, which lives in the main CPU. You can think of it as the boss of the whole operation. Its job is to select one of the two PIO cores, then choose which state machine it wants to use. It then hooks up that state machine to the GPIO pins it wants it to control, before finally loading the PIO program onto the state machine. So how can the main C program load the PIO program onto the PIO core? The Pico SDK provides a library of functions that allow a C program to communicate with the PIO core, but how can the C program read the PIO program? After all, they're written in different languages. Well, that's where CMake comes in. In our CMake file, we can run a function provided by the Pico SDK called Pico generate PIO header, which reads the contents of our PIO program and converts it into a C header file, which our main C program can read from. This C header file contains a translated version of the PIO program, as well as some important functions for initializing and giving commands to the PIO program. So first, how does this function translate the PIO program into something readable by the C program? It takes every instruction, converts them into numbers, then saves them in sequence inside of an array. Then it creates a C structure with the type PIO program and saves the array of instructions as one of its values, among other things. And just like that, the PIO program is now stored in a representation that the main C program can understand. When the main program loads the PIO program onto a state machine in the PIO core, it will use a pointer to this structure as an input parameter. Now let's talk about the functions in the header file. Where do they all come from? Well, in our PIO program, we can actually embed some C functions at the very end by surrounding them with brackets and using the C-SDK prefix. The CMake function will copy these C functions verbatim into the generated C header file. Now, technically, you could save these functions in your main C program, but saving them inside the PIO program makes it more portable. You could write one PIO program file, then use CMake to generate a single header file, and then reuse that same header file in multiple projects. Now let's quickly walk through the process of loading and starting a PIO program to add a UART transmission port using, say, GPIO pin 3 as our transmission pin. The main program will first call the function PIO claim free SM and add a program for GPIO range. It's a mouthful, but it clearly states what it does. It finds any PIO core with a free state machine. They're all the same, so no need to be choosy, and then loads the PIO program onto that state machine. It then defines the range of GPIO pins the state machine will access by providing the lowest GPIO number required and the number of GPIO pins. Since we only need to access one GPIO pin, we set the lowest GPIO number to be our transmission pin, and the number of GPIO pins to be 1. Then it runs an initialization function, which was embedded in our PIO program and copied into the header file by CMake. Now, looking at the PIO program, you might notice that the instructions that interact with the GPIO pins do not reference any pin numbers. That's because we set up which pin numbers each instruction can access in the initialization function. We take all the GPIO pins a state machine has access to and categorize them into 4 groups of pins, which are the set group, the out group, the in group, and the side set group. the pins in each group are referenced by the relevant PIO instruction using the simple label pins. So let's say that our pin number 3 is put into the set group. Then the PIO instruction set pins 1 will set the output of pin number 3 to be high. Or let's say we put pin number 2 into the side set group. Then every time we run a side set command, it will automatically set pin number 2 without us having to reference the pin number every time. Since our UART transmission PIO program only makes use of the out and side set instructions, and both of them only need to manipulate one GPIO pin, or transmission pin number 3, we can set both of them to be the same pin. There are other things to configure, but to keep the video simple, I'm only highlighting all the pin-related stuff. Finally, we initialize and start the state machine. Now that the state machine is up and running, the PIO program is waiting for data to transmit. The main function can send data to the state machine using the last two C functions defined in our PIO program file. First, a function for transmitting a single character. All this function does is push a character into the transmission FIFO of the state machine using PIO-SM put blocking. Using this function, we can create another function for transmitting a string, which runs our single character function in a loop. And that's a very simple, high-level overview of how a Pico project written in C can make use of the powerful programmable I/O feature.